discussing about two-dimensional steady state heat transfer, conduction heat transfer. So in that we discussed that we need to solve this equation numerically. So it means that first of all we need to create a grid, and then we need to write this equation on each node of that grid, interior node of that grid. So in the last class, we discussed about two methods. One was finite difference method. So in that we discussed about nodal network, that how can we discretize the equation by using the finite difference approximations. So we did that. Adderley, do you want to add something? Maybe not. Uh, so I am muting you at the moment. So uh, if you have got any query, please ask by unmuting your mic. So we were discussing that in the last class we discussed about nodal network, and then in the nodal network there are some limitations that it is only applicable to Cartesian grid, and then boundary condition application is difficult for this case. So then we discussed about finite volume method, which is the energy balance method. So in that we discussed that we assume that all the energy is going into that principal node, and for the conduction energy we know that we can use Fourier law to determine that E in for each node. And then this is the equation 175, which we discussed that here because this neighboring Mn principal node, it has got four neighboring nodes. We can send it the heat into this node. So these are the four nodes. And then the second term is the volumetric heat generation if that phenomena is present in that body. So then that determination of those heat transfer rate, they are quite straightforward. The rule of thumb is that whatever the principal node that would come second in that difference, here as it is shown that Tmn is coming second in that difference formula, because we are assuming that all the energy is coming in, but of course it is not true, because in the end when we would calculate all the temperatures, so some energy would be going out as well from Tmn to have that steady state operation. If all the energy is coming in, then this principal node would have a transient behavior, which means that the temperature of this would increase with time, which is not the case in the steady state heat transfer. So we discussed different cases, convection, how to handle convection. That is by using the Newton's law of cooling. And then in the end of the class, we did one numerical for this energy balance method that was from the some electric bus bars. So we discussed this thing. If you have got any query from the previous lecture, you can ask. Otherwise, we can continue with the numerical problems for the energy balance method. So if there is any query, please ask now. So it means that everything is kind of okay, because there is no query at the moment. So we continue with the numerical problems for the energy balance method. Now we can see a triangular edge cutting tool edge. Now there is a node at the corner of this cutting tool edge, which is node Mn at the tip of a cutting tool, with the upper surface exposed to a constant heat flux, which is given by Q naught double prime, and the diagonal surface exposed to a convection cooling process with a fluid at T infinity and a heat transfer coefficient H. Now assuming uniform grid, which is delta x is equal to delta y, derive the nodal finite difference equation at node Mn assuming steady state heat conduction. Right, so we need to write the finite difference equation by using the energy balance method. So first of all, if we try to see that what would be the area of influence for this node Mn, so the midpoint between Mn node and M plus 1 N node would be somewhere here, and then on the diagonal surface the midpoint would be somewhere here. So it means that the area of influence would be is this triangular shape, small region. So I kind of show that region here because now you can see that area of influence which is shown in this gray shade. So this is the midpoint between Mn and M plus 1n, and then on the diagonal surface this is the midpoint. It is kind of approximate. So now we have got three heat transfer process which is occurring for the node Mn, the area of influence of the node Mn. One is the conduction through M plus 1 N. The second one is the convection which is happening in this perpendicular direction, and then the heat flux which is coming from the top. So if we apply the energy balance, and then because there is no volumetric heat generation in this case, so first of all if we want to determine the a in this diagonal area, we all know that we can use Pythagoras theorem, and that is basically uh, perpendicular square plus base square uh, whole under root. So if we do that, because this distance is delta x by 2, and this distance which is this, that is delta y by 2. So if we kind of determine this diagonal surface value, that would come out to be equal to under root 2 into delta x by 2. So if we apply the energy balance, we can see that one is the conduction heat transfer, one is convection, and one is heat flux. So now we would continue with the discussion which we did in the last lecture, that if we want to calculate the conduction heat transfer for from the node M plus 1 N to this area of influence of Mn, that would be equal to K into, now area available is delta y by 2, which is half of the total delta y, which would be from total delta y would be like this. So this is kind of half of that, and into one is, again I would repeat that it is the unit thickness or unit width into the bone, and then Tm plus 1n is coming first, minus Tmn divided by delta x, which is the total distance between these two nodes. So this was conduction heat transfer. Then if we want to calculate the heat flux, if heat flux is given like Q naught double prime, so we want to calculate the total heat transfer. So it means that we need to multiply heat flux with the area on which it is being incident. So in this case, the area would be this area of influence. This side would be delta x by 2 into 1 again unit thickness. Now for the convection, the convection heat transfer, we all know that we can use Fourier law of Newton law of cooling. So in this case, because heat is going in, so now it is kind of other way around, that T infinity minus Cmn, and then this first uh, area of calculation, this first length is this diagonal length, which is between M plus uh, from here to here. So that we have already determined on the last slide, and then it is under root 2 into delta x by 2 into 1. And if we put in the values for all the this is the heat flux from the top, heat transfer rate due to that, and then we have got the conduction heat transfer from the right hand side node, which is M plus 1 N, and then in the last term, that is the convection heat transfer from the surrounding fluid. So if we put it that equal to 0, so then we can rearrange it in terms of T M plus 1 N. T infinity Q dot Q naught double prime delta x by 2 minus 1 plus under root 2 into h delta x upon k into Tmn. So can anyone tell me that what terms for in this equation would go on the right hand side of the equation? There are four terms: Tmn, T infinity, then Q naught, and then in the last one is the Tmn term. So which term would go on to the right hand side of the equation?
T T infinity.
T infinity. Thank you, Jayad. Anything else that can go on the right hand side?
Q naught.
Q naught term, because that is also given to us, that would be given to us. So it means that in this equation we have got only two unknowns, which one is Tm plus 1n and the second one is Tmn. So, because in this course we are not going into the numerical solution of these, uh, we would only talk about the formulation of those equations. Now, once those equations are formulated, then we can, of course, we can use the different iterative method to solve those equations. So if you look at your chapter number 4 of the book, so in the first part they have talked about nodal networks, then energy balance, and in the second part they have discussed that how they can solve those equations which were formulated by energy balance method or nodal network, how they can be solved to calculate the values of these temperatures at these nodes. So that is something which we are not going to do in this course, because that is something you have already done in your math course. So we are not going to repeat that here. Instead, we would give you a project in ANSYS, so it would give you a little bit better skill set in terms of the solution. Okay, when we do the iterative solution on a piece of paper, it is the kind of very laborious job. You can do quite limited iterations, but because all these algorithms are being incorporated in a software, so it would be better to learn that software. So I would assign a project to your class. So all the terms and conditions of those projects would be explained in that mm, project statement. So hopefully by the end of this week you would be assigned that project, and you would be given ample time to do it, like maybe 6 to 8 weeks. So don't worry about that. And it would be a group project, but how to make that group, I would have some conditions for that, so I would communicate that in due course of time. Okay ji, now the next problem here is energy balance method. So for the energy balance method, because we have already studied the fin analysis, one dimensional fin, so we are going to do one more numerical for a cylindrical or pin fin. So a steady state finite difference uh, analysis has been performed on a cylindrical fin, uh, which is also called a pin fin, with a diameter of 12 mm. So diameter of this cylindrical fin is given, and a thermal conductivity of 15 watt per meter square Kelvin. The convection process is characterized by a fluid temperature of 25. It means T infinity is 25 and H is also 25 watt per meter uh, watt per meter square Kelvin. So this is T infinity, which is 25 degree, and this is H value. And now if you look at here, they have given you the temperature of T naught, T1, T2. So T3 is unknown. So if we look at the part 1, the temperature for the first three nodes are given, right? So now we need to determine the fin heat transfer. So one way of doing that is using that table which we discussed in chapter number 3. So second way is by using the finite difference equation or the energy balance method. So we are going to do that if we want to calculate the heat transfer from here from fin, so that would be equal to QB. So which is the heat transfer. So if we apply the energy balance at T naught, then we can get one is Q convection, which is coming in, then one is Q1, which is coming from T1, because we are taking energy balance, so all the energy would be going into this node 0. So that is something which, if you see here in the schematic, they have shown that QF is the heat transfer which we need to determine. QCV is the convection heat transfer which would be coming in. So in reality, it would go out because due to assumption of heat, the energy balance method, we take all the heat coming into the node. So if we kind of apply the energy balance method at node 1, so we can write QF plus Q1 plus QCV is equal to 0. So QF is something which we need to determine in part A. Q1 is the heat which is coming by conduction from node 1, and QCV is the heat transfer by convection. So from here we can write QF is equal to which is the desired heat transfer which we want to determine, that is equal to minus Q1 and minus QCV. So Q1 would be equal to K into AC. Now, what is the AC for this cylindrical fin? That would be equal to pi d square by 4, and then you can see Q1 is equal to T1 minus T naught. So uh, now AC would be equal to pi. That is the cross sectional area of a cylinder or circle. So that is pi d square by 4, एंड देन टी वन माइनस टी नोट, और उनके बीच में जो फासला है जो 1 and 0 नोट के, वो डेल्टा एक्स है, तो वो यहाँ पे आ गया. इसी तरह क्यू सी वी के लिए एच इंटू ए एस. नाउ द इफ यू सी द area of influence is this length is delta x by 2, because this is kind of a boundary node, right? So the area of influence would be half. If this is the total distance delta x between node 1 and 0, then this is the area of influence, which is delta x by 2 into pi d. Pi d is the circumference for that cylinder. So pi d into del x by 2, and that is T infinity minus T naught. So all we need to do is that put in these two values in equation 190 and then put in the numerical values. So if we put in the numerical values, like K value is given 15, and then T1 is given in the data, that is 93.4, and then T naught is also given 100, which is here, and then 4 into delta x is given as 0.01. So that is there, and then pi by 2 dh value is also given 25, and delta x again 0.01, and 25 minus 100. So from here we can calculate QF. So that would be equal to 1.473 watt. Now this was part A. So I hope that this is clear to all. Now if we go back and see that what is part 2, that is determine the temperature at node 3. So now because node 0, 1 and 2 are given, but node 3 is not given. So the problem statement wants us to determine the temperature at node 3. So if we apply the energy balance method at node 2, then there would be a heat transfer from node 3, which would be equal to Q3, and one heat transfer would be coming from T1, which is Q1, and then one is coming from the convection. So for the if we draw the area of influence, it would be total delta x here, because it is an interior node. So if we see the schematic here, now you can see the schematic here, that for the node 2, if we draw the area of influence, it is the this length is total delta x for this. But for this boundary node, it was delta x by 2, because it was kind of a boundary node. But for the node 2, it is complete delta x length here. Why is that? Because it is an interior node. So uh, now if we apply the energy balance for this, again we can write the energy balance. QCV is the Q convection, which is this here where the mouse cursor is, and then Q1 is the heat which is coming from node 1 into node 2, because 2 is the principal node. So all the heat we would take it to come inside this node, and then another heat would be coming in into node 2 from node 3 by conduction. So QCV is the convection heat transfer, Q1 and Q3 are conduction heat transfer. So if we calculate Q1 and Q3, very easy, K into AC. AC is the cross-sectional area of this fin, which is pi d square by 4. And then because Q1 is going into node 2, so you can see that T2 is coming second in that difference formula in the numerator side. And then for the Q3 as well, K into AC, again AC is pi d square by 4, and then T3 minus T2, because again the heat is being transferred into the principal node. So on the same lines, if we want to define QCV, that would be equal to HA into T infinity minus T2. Or maybe it is a little bit wrong here. It should be T2 rather than I think I have corrected it here, but in the first formula where T naught is written, it should be T2, right? So it shouldn't be T naught. So I would make that correction when I would give you the slides today. So here it should be T2. Please don't be confused. It should be T2. Here. So I have corrected it in the second step where I have shown h into p into delta x. Perimeter of a circle is I into d, and delta x is the this length of where the influence of node 2 is. So QCV is this. So if we put in the values, so first one is convection, and then the only unknown in this equation is T3. So we can take all other terms on the right hand side, and then we can calculate T3 from here. So if we rearrange for the T3, it would be equal to minus T1 plus 2T2 minus this whole term which involves the convection, right? So because all the values perimeter pi d and del x is given, K into AC we know pi d square by 4, T infinity is given, and T2 value is also given in the data, which is 89.5. So we can calculate T3, which is equal to 89.2. So if you see that the values of T naught, T1, T2, so they are being decreasing from 100. So 100 is for T naught, T1 is 93, which should be less than this because heat is coming out of uh, heat is being lost from this fin by convection. So node 2 has 89.5, and then for the node 3 it should be less than 89.5. So if we see here it is 89.2, so it is physically correct value. Numerically we can have the physical interpretation if we try to build. So the due to the finite thermal conductivity of this fin, the temperature should decrease as we move along the fin tip, right? So that is the thing which is we have seen here, that its value is 89.2 degrees centigrade, right? So these are some of the problems which you need to do at your own time. They are from chapter 6th edition for the Incorporated book. So now we can have 5 minutes break, and then at 10 past 4, the quiz number 2 would appear on in your assignments. So you would have 15 minutes to do it, and then you have 5 minutes to upload it in the same assignment, and don't forget to press the button of turn in, because when once you press that button, then that is submitted. Otherwise it only appears to me that it is viewed and there is no time of submission. So please don't forget to press that turn in button for that quiz number two. Right. So I would give you 5 minutes break. If there is no question from this lecture, then you can have 5 minutes break and prepare for the quiz. So, is there any question? Okay.
No, sir.
Okay, Ji. Thank you. So you can have your calculator and that piece of paper ready, and and then you can have the quiz in 5 minutes time. Good luck. Ji Zara Khan, anything you want to add?
Yes, sir.
जी कोई क्वेश्चन है आपका?
No, sir. No, sir.
अच्छा चलें फिर म्यूट कर लें. Okay, ji, you don't need to write your name in the chat window because I am going to download the attendance. So anyone who has attended this meeting, then that would be present. So assignment should be visible to you, the notification for that. So can anyone
जी सर
confirm
आ
that?
गया
Okay, ji, you can continue with that. So I won't take much of your time. Okay.